Hello everyone, this is Dr. Webb, and this is it. We have reached the culmination of the course. This is the climax. We are going to talk about the fundamental theorem of calculus, and we are going to focus in on what's called part 2 of the fundamental theorem of calculus. We will prove part 1 in the next video. It turns out you actually can prove them in either order. So before we jump into that, let's review some definitions and facts that we proved in the last video. So we've been working with these Riemann sums, and so if we can take the limit as n goes to infinity of these Riemann sums, and this limit makes sense, then we say that the function is Riemann integrable. And we use this notation for the definite integral, where we're taking the integral from a to b of our function f of x, and this dx, this is called our measure. This is what we get from this taking the limit of these Riemann sums, right? And the important factor here is that when we take this limit, it does not matter how we choose these x values inside each subinterval. It just has to be any value inside the subinterval. We end up getting the same limit. That's going to be important later on in this video. And then we also saw that if a function is continuous on the interval a to b, then it's going to be Riemann integrable. Okay, and so continuous functions are one example of a group of functions where this makes sense. So let's move on to the fundamental theorem of calculus part 2. Okay, so in this we're starting off with, we're going to let f of x be continuous on a to b, so this means that it's Riemann integrable on a to b. And then we're going to take some other function, we're going to call it big F, and we want it to also be continuous on a to b, with the added caveat that it's also differentiable between a and b, and that its derivative is our little f of x for any point inside these two. Okay. Then, if we take the definite integral of little f from a to b, the value of this integral is going to be just plugging in the endpoints of big F and taking the difference between them. So the important thing to note here is the values that we're plugging in to f are coming from the endpoints of the integral. Okay, so if we're taking the integral from a to b of little f, that's going to equal big F at b minus big F at a. And this works for any big F such that the derivative of big F equals little f. Okay, so this is what the fundamental theorem of calculus part 2 is saying. So any big F in which has this true, such that big F, the derivative of big F is little f, these are called the antiderivatives of little f. So big F here is called an antiderivative of f of x. And so what the fundamental theorem of calculus is saying, so what FTC is saying really is to evaluate definite integrals we need to find these antiderivatives. Okay, so let's do an example like this, right? So here we're trying to integrate from 0 to 6, just the function 2x dx. And the nice thing about this integral, remember one of these things, properties of these definite integrals is these give us the area under the curve. And this, geometrically, we actually can figure out this area. So what's going on geometrically here? Well, the line 2x goes through the origin. And so if we go out to 6, this is going to end up going through the point 6, 12, right there. And then this definite integral is giving us the value of the area of this triangle right here. And this triangle has base 6 and height 12. And so the area is equal to 1/2 times 12 times 6, which if you work this out is going to give you 36. Now, what does the fundamental theorem of calculus have to say about this definite integral? Well, what the fundamental theorem of calculus says is that if I can find some function whose derivative is 2x, then I can use that to evaluate the integral. And I can think of such a function. If I let big F of x equal x squared, then it's pretty easy to check that its derivative equals 2x. And that matches what we have inside the integral. And so the fundamental theorem of calculus then tells me to integrate 0 to 6 of 2x dx, this is going to equal, well, I take my big F and I take the difference of it between the two bounds. And so the notation that we often use, shorthand for this difference right here, would be take f of x, take the value at 6, and subtract off the value of 0. So this notation is the same as this. And so that's the shorthand that people often use. And let's actually plug this in. Plugging, we get 6 squared minus 0 squared, which, as we see, gives us 36. Okay, and so these two values match, and the fundamental theorem of calculus has worked. Okay, so why is this work? Why can we use this trick? Okay, so let's start off like we're doing a Riemann sum. We're going to need to use them at some point. And so let's just take any n greater than 0, and then we calculate out our width of the subintervals. That's going to be delta x, which is just going to be b minus a divided by n. So these are just our widths, the same as we've been seeing before. And then we're going to start off just looking at the difference f of b minus f of a. And through the course of this proof, we're going to show that this difference is equal to the limit of these Riemann sums. You know, it's going to give us this definite integral we've been looking at. And so the first step that we're going to do is we're going to add 0 a whole bunch in between the f of b and the f of a. And we're going to do this in a clever way. So what we're going to do is we're going to evaluate the function at each of the endpoints of these subintervals, but then we're going to subtract them off from themselves, right? So we're going to cancel them off. So really in each of these parentheses here, we're adding the value at one endpoint and then subtracting it back off. So that's equal to 0. That's equal to 0. And so we're really not changing the sum at all. So it stays equal. This is what we have in between. Now that we have this, we are going to rearrange it a little bit. And so I'm going to take this minus f of a plus n minus 1 delta x, and I'm going to group it together with f of b. And then I'm going to take this other one and group it together with the part that's getting subtracted from the next one. Right? So I'm going to keep with that pattern, and then in the last one, this bit is going to get connected to what happened in the one before, and then this last one, f of a plus the single delta x, that's going to be connected with f of a. And so when we rearrange this, this is what we end up with. Right? So it's f of b minus f of a plus n minus 1 delta x plus f of a plus n minus 1 delta x minus f of a plus n minus 2 delta x plus da-da-da-da-da. Continue that all the way down the line. So the last part is f of a plus delta x minus f of a. Okay, and so really what's going on On each of these, we're taking the difference between the between the endpoints of the two subintervals, right? And so when we add this all together, all the subintervals in between, they all cancel themselves off, and so we're left back with f of b minus f of a. Now, in jumps the mean value theorem. So we talked about the mean value theorem a couple of videos ago. And so just to recall, the mean value theorem says if big F of x is continuous on a to b and differentiable from a to b, and so we have that in our case, then there exists some x value c between these two such that the derivative, the value of the derivative of f at c is equal to, well, we take the difference of big F between the endpoints and then divide by the length between them, divide by b minus a. Okay, and so right now this is written for doing this on the whole interval, but actually we're going to use this on each of the subintervals. And so we need to rewrite how we're actually going to use this. So here's the mean value theorem that we're going to use right now. Okay, and so we're going to start off the same way. We have our big F, and it's continuous on, but we're going to be thinking about this just on each subinterval. And so the subintervals are going from a plus k minus 1 times delta x to a plus k times delta x for some k between 1 and n. So that's the interval that we're focused in on. And so then it's also going to be differentiable in between, and this works for our big F because it's differentiable on the whole interval from a to b. And so then it says there exists some x value. Well, now it's not between a and b, it's actually specifically between these two x values. So we're going to call that x value x sub k, and it's going to lie in between these two endpoints of each subinterval. So this means that we can take some value x sub k, and this is in the kth subinterval. And so then what we're left with then is that the value of the derivative of f at x sub k, well, it's going to equal, we're going to get a fraction. On the top, we have the difference of f at the two endpoints, right? And then underneath it, it's going to be the length of this. But how long is this interval? Well, we're going from a plus k minus 1 delta x just to a plus k delta x. So how far have we gone from one endpoint to the other? Delta x. And so rather than be dividing by b minus a, the length here really is just delta x. So we're just going to plug delta x here. And this is the form of the mean value theorem that we're going to use. So here it is, mean value theorem that we're going to use. Okay. Now we're talking about the derivative of our big F evaluated at x sub k. But what do we know about the derivative of big F? Well, we know that the derivative of big F is actually little f. And so this is equal to little f of xk. And then for the mean value theorem, it's equal to this fraction. Okay. Now what we had in our sum before was actually a bunch of these added together, not divided by delta x. And so let's just get that by itself. Let's multiply delta x on the other side. Then what we're left with is f of xk, so little f evaluated at the special value in between the two endpoints, times delta x is going to equal to the difference of big F at these two endpoints. So this is what we're going to use. And so let's carry it through. So we have little f evaluated at x sub k times delta x is equal to the difference of big F evaluated at these two endpoints. And so this little xk, this is the special value coming from the mean value theorem. So I'm not picking any x sub k here, I'm picking the special value given from the mean value theorem. But what's important is that it is a value in between there. Okay. And so when we look at our sum that we started off with before, we had f of b minus f of a. Remember, we added a bunch of zeros, rearranged it, we were able to rewrite it such that it's big F evaluated at these endpoints and then subtracted from each other. and there's a lot of cancellation going on. But now each one of these, so f of b, remember b really is a plus n times delta x. And f of a plus x minus f of a we can really think about as being a plus 0 times delta x. And you see that each of these differences here look exactly like these differences that we get from the mean value theorem. And so we can substitute in for each of these differences the appropriate f of x sub k times delta x. So this first one is going to be f of x sub n times delta x. Next one is going to be f of x sub n minus 1 plus delta x. And we do this all the way down to the last one, which is going to be f of x sub 1 times delta x. Okay, so let's write that in nicely. And so we have f of b minus f of a is equal to f of x sub n times plus delta x, all the way down the end to f of x sub 1 times delta x. Now each of these x sub k's in here are coming from that subinterval. So what is this? This actually is a type of Riemann sum. So what happens? We can do this for any n. So we can talk about taking the limit of this as n goes to infinity. Right? So here it is a Riemann sum. Now let's take the limit as n goes to infinity of both sides. Now on the left-hand side, there's no n's here between f of b minus f of a. It's just a constant. And so taking the limit doesn't change anything. So it's just going to stay the same. On the right-hand side, well, this looks like the definition of a Riemann of a definite integral. And we started off with our little f being continuous. And so that means that this is Riemann integrable. And so we do have a definite integral here. So applying this limit on both sides, we end up with f of b minus f of a, because the limit on the left, we're just taking the limit of a constant. So the limit isn't changing anything. On the right-hand side, we have our integral, our definite integral from a to b of little f of x dx. And that's it. That's the fundamental theorem of calculus, part 2. So here it is again. The key part here, and this is the crazy thing about the fundamental theorem of calculus, and it says that this integration, this finding areas, this is closely related to derivatives, which was finding slopes of tangent lines, right? And so what the fundamental theorem of calculus is saying deep down is that these are sort of two different sides of the same coin. That on one side you integrate, on the other side you differentiate, and they're really sort of, one is undoing each other. They're almost kind of inverses of each other. Okay, and so we will talk more about this in the next video, where we will talk about part 1 of the fundamental theorem of calculus and some other associated facts. So I will see you again soon.